Hello, in this video, we're going to be talking about active transport. So let's not waste any of your time. Let's get right to it. Now, when we're talking active transport, okay, the one thing that we have to remember is that we are leaving behind those passive transport principles, and now active transport has its own set of principles. And you can look at it in one way is that it's the exact opposite. So in other words, we are going to require energy for this transport, and we're going to be going against the concentration gradient. In other words, we're going to be going uphill. Okay, and one of our examples that we're going to use is a restaurant. Okay, now if you know me any at all, you know that I'm all about the food. I'm a foodie. I like making it, whether it's smoking, whether it's grill, in the kitchen, whatever. I just like making good food, and we enjoy going. Actually, we don't go. We usually get it and take it home. But good restaurants. So, but if you think about a restaurant, you know, if you go to a restaurant and you look in the pantry, you look in the refrigerator, you look in the cooler, you look in the freezer, you're gonna find a lot of food. Okay, a lot of food. But what you'll also find, if you look around, is you will find that they've already ordered a whole bunch more food. Now, why would that be? Well, obviously you can think of is that the food that they have is for today, maybe tomorrow, maybe the next day at the most. But they got to think about beyond those days. Okay, they've got to take into account that if they place an order, maybe it's 4 days before it actually arrives. So they can't afford to run out of food and then go get some more food. For one, it potentially would be cost-wise counterproductive if they just went to the grocery store as opposed to their wholesale delivery service. But they've got to think about the future, and your cells the same way. So active transport, when we say it goes against the concentration gradient, what we're saying is that we've already got a bunch, but we're bringing more in. Okay, but that's going to cost us some energy to do that, because we're talking large molecules. Okay, big stuff. Okay, and that's the idea of with active transport. Now, another thing to think about the active transport, it has to be happening all the time. Okay, because diffusion causes that. Because diffusion is constantly moving substances back and forth, trying to equalize everything, whether it's a particular element or molecule, or it's because of the electrical gradient, ions, plus or minus, positive or negative, inside or outside of the cell. Because diffusion is doing all of that, then active transport has to be moving to keep things in check all the time. Active transport uses quite a few different, just like facilitated diffusion, use quite a few different proteins. Active transport does the same thing, and we'll get into all that, but uniporters, symporters, antiporters. We've got the sodium potassium pump that we're going to be looking at, and the whole idea with coupled transport. That's a huge concept for you to grasp, and an important one for you to grasp. But we'll talk about that when it's time. Alright, the whole idea of active transport. Again, we want to emphasize those principles. It requires energy. Okay, and that energy source is going to be ATP. ATP is going to supply the energy for whatever the transport is going to be, and we're going to move substances from a low to high concentration. Passive was the other way, high to low. In other words, we're going to be taking things that there aren't, where they're not much, to areas where there's already a whole bunch. Okay, and it's going to have to take the proteins we're going to use have to have certain skill set, just like the actor in Taken would always say. I've got a particular skill set that I use, and these proteins are that. And again, we're thinking restaurants. We're thinking about, we've already got a bunch, but we're bringing more in because we got to think about the future. All right, our first concept that we're going to think about is the sodium-potassium pump. And the sodium-potassium pump is huge when you're talking about your neurons. Matter of fact, one of our day 2 activities, or at Crowder, just one of our activities in class, are going to be to look at a simulation of a neuron and to see this process. Also, by looking at this diagram, we're going to be able to kind of really emphasize that electro gradient as well as that chemical gradient. Okay, but if you look at this diagram, okay, the left side, that's outside of the cell. Okay, and you can see all those sodiums there, and you got the one potassium. And if you add up the positives, okay, and then add up the negatives, which is the chlorines, there's going to be more positive ions than negative ions. So therefore, the outside of the cell is a positive charge, and you can see that at the very, very top. Okay, now inside the cell, and the very first time I looked at this diagram, 100 years ago, and looked at it, at first glance, you're thinking, wait a minute, how could the inside be negative? Look at all those purples. I mean, we got a whole bunch of them there. Just a few A's, a couple of chlorines, even got a sodium in there. So you're thinking, how could that be a negative charge? But you got to look closely at the A's. They've got 4 negative signs. It really means that's a macromolecule that's got a carbon backbone, and it's got all kinds of things attached to it, and it's in 4 different negative charged molecules. So if you add up all the positives and subtract all the negatives, you're going to get a negative number. So the inside of the cell, in this case, is negative, and it always is negative. I mean, it does reach a positive number when a neuron fires, but under normal conditions, a cell just is negative, and that's just the way it is. But a sodium-potassium pump, especially when it comes to your neurons, alters that and provides that kind of that burst of energy that comes through as the neuron fires, and causes that change so the neuron can be passed on to the next neuron. But what happens essentially is the gateway initially opens up, and the sodiums move in, okay, because sodiums want to move in. They're using essentially diffusion to try to balance out not only the sodium difference in amounts, the concentration amounts, but also the charge difference. It's trying to make that cell be neutral, okay, to be neutral. And they just move across and trying to do those 2 things. Now the potassiums, okay, they're also a positive ion, but they respond a little bit differently. They tend to be more equilibrium friendly ions, because not only will they chase out the sodiums, but they'll also leave themselves, okay, which reduces or returns the ion back to its normal resting state. Like a neuron, normal resting state is -70 on the charge. And as those sodiums go pouring in and the potassiums go pouring in, it'll get up to like that positive 130, 135, but then they go roaring right back out to get it back down to a normal resting area. But the idea is that you got 2 factors that can be determining the movement of ions. The ion amounts themselves. Okay, are there more outside the cell than there are inside the cell, or vice versa? And then they'll move in that direction. Or the charge of the two areas. Positive on the outside, negative on the inside. So therefore, positive charges are going to be moving into to try to equalize that or bring that down to a neutral setting. Alright, so in this process, active transport, we're going to use 3 types of proteins. And these types are basically named after their function. Okay, but when we're going to move things, if we use a uniporter protein, then that's going to move one molecule at a time in one direction. Okay, a symporter, S for symporter, S for same, as in same direction, we're going to be moving 2 molecules in at a time. Okay, just like we talked about that saturation rate, where now we've got double the amount going in and in the same direction. Okay, now the antiporter, or A for antiporter, A for against, science has this lovely process to where if they need a word for being the opposite of what they just described, there's not really a word, then they just put the letter A on the front of it, like there's biotic and there's abiotic. So they put the word A on the front of it, and that means the opposite. But an antiporter is going to move molecules in different directions. Okay, so you can think of the first one is like a city street, just a car every now and then coming through. And then the second one, you can think of like a divided, a city or a 2-lane road where 2 cars can go through at the same time. And of course, in the antiporters, those big highways where they're split and you got multiple things going through in multiple directions. So that's our video for active transport. The next time we get together, we'll be talking about primary and secondary transport. We'll see you then.